Hi everyone. Imagine this situation. You have a lot of cordless power tools, for example, 18-volt ones, and you need a compact, small-sized battery that can handle any power tool, can work in severe cold, has a lifespan not of a measly 800 to 1000 cycles like classic lithium, but around 8000 cycles, is safe, and, if necessary, can be charged in 10 to 15 minutes. And it's not a huge multi-tiered battery, but just a single-layer pack using 21700 cells. This is possible if you use lithium graphene. I talked about the features and advantages of this technology in a dedicated video, which you can watch via the link in the description. So, I have a pretty powerful battery pack built with 18650 cells in the Upsell U30, the same Molisol P30B, and at the time this battery was assembled, there was nothing better available. But now there are 18650 cells with resistance of less than 3 milliohms, and this beauty, even though it's still top tier, is already outdated in terms of discharge current. Nevertheless, it's soon going to be used in another interesting project and won't be with me very often, so I wanted to make something similar just for myself. It was important for me to make a compact battery with high discharge current with the ability for fast, unbelievably fast, charging, which, among other things, would be used, so to speak, in the field. It will be charged either from a car battery through a powerful converter, or with a gadget like this one. This is also a converter, the design of which I showed in this video. Input voltage is supplied from a smartphone charging adapter or a power bank, and it easily charges almost any battery. This charging system is nothing more than a boost converter with output voltage stabilization and charge current limitation. It's built on a CN3300 driver and two powerful MOSFET transistors. The input voltage can be as low as 5 volts. For efficient operation, I recommend supplying 12 volts. The maximum rated power is 40 watts, but you can go up to 60, which is about 3 amps of charging current. The device will charge the battery up to 21 volts. After that, the charging process will shut off. By the way, there's also an LED charge indicator on the board. This board is convenient because it allows you to charge a 5S battery from a smartphone charging adapter. In my project, a power delivery trigger is used at the input of the converter, which requests 12 volts from the charger. The device is assembled on a double-sided printed circuit board. The bottom part is a solid ground plane and serves as a heat sink. The printed circuit boards are factory-made, ordered from our sponsor, JLC PCB. This is a leading manufacturer of printed circuit boards that can bring any of your projects to life. The company can produce printed circuit boards of any size, shape, and number of layers. Thanks to a complete production cycle, thorough quality control is carried out, ensuring that the quality of the boards is always at the highest level. Ordering boards is very convenient. You just upload the Gerber files for your board, specify the required options, board thickness, copper thickness, trace coating, choose the solder mask color, and that's it. There are many additional options that will allow your boards to comply with all European and international directives. The prices are very affordable. Just $2 for a batch of 5 boards size 10 by 10 centimeters, and for 6-layer boards, there's a $30 discount coupon. JLC PCB is easy to use, affordable to manufacture, and reliable in operation. The link is in the description. That's all for the charging system. You can watch a more detailed video by following the link in the description. Graphene isn't cheap, but the high cost is fully offset by the claimed lifespan of 8000 cycles. Whether they'll actually last that long is still unclear, since there haven't been any endurance tests yet. But let's hope the manufacturer isn't exaggerating. They can be charged at currents of 5C with a capacity of 4.2 amp hours, which, just for the record, is 21 amps, and they don't heat up much in the process. The manufacturer claims 8000 cycles, specifying a charging current of 5C and a discharge current of 3C. Their maximum discharge current is up to 25 to 30 amps continuously, and up to 50 amps for short bursts. So, the task is to build a high-current battery capable of short-term discharge currents of 40 to 50 amps. Ideally, the fastest possible charging would be from 0 to 80% in 10 minutes, with the ability to operate in freezing temperatures of minus 20 degrees and below. In theory, graphene is much more effective than conventional lithium at such temperatures and can function down to minus 35 or even minus 40 degrees. The battery should have a good protection board, a reliable casing, and be able to easily power all 18-volt power tools, even the heavy-duty ones like impact wrenches, angle grinders, and powerful leaf blowers, which can draw currents of 50 amps or more from the battery. And that, just for the record, is a kilowatt of power. I bought these graphene batteries a long time ago for a review, and since then they've been waiting for their moment. I got 5 of them for a reason. That's exactly how many you need to build an 18-volt battery pack. The internal resistance of the cells is about 4 milliohms, which is really impressive. To start, I connected all the cells in parallel and left them for a few hours to balance. In the meantime, I had to think about the case. Of course, you can just buy a ready-made kit, and they're pretty cheap. But why bother when you have a 3D printer and some great folks who share their models for free? I downloaded a case model from Philips. I think these are the best models for Makita-style mounts on the whole internet. Next up, slicing and printing. No need to add supports at all. The author already took care of all that. I chose ABS plastic for printing, even though PG is more resistant to low temperatures. But ABS is still a strong material and, most importantly, it's heat resistant, with a high softening temperature. After a few hours of printing, all the main parts were ready. Next, I decided to show off a bit and add some printed nameplates of my own to make it unique. At this stage, we only need the holders, put everything else aside. The problem is that the diameter of these parts is larger than the standard 21-700, so they didn't fit into the holders. I could have modeled new ones, expanded the old ones, or tried to force the parts in by heating the holders. But I just cut off part of the heat shrink from the parts, and everything fit perfectly. The BMS board. Obviously, for currents of 50 amps and above, small protection boards just won't cut it. You need something more serious. That's why we take a board like this one, with 6 powerful MOSFETs on board and, most importantly, with very serious power terminals. Here's a comparison of what they look like on cheap but decent boards for mid-range power tools versus a high-power board. Here, first of all, there are more current-carrying contacts, and secondly, the metal is thicker and the current capacity is much higher. After that, we additionally solder all the terminals from both sides, as well as some components where the Chinese manufacturers skimped on solder. Even though the power traces on this board are quite wide and doubled up, there are still a couple of spots that should be reinforced. To do this, I first removed the solder mask, then reinforced it with a double layer of 0.2mm copper tape, and afterwards, for aesthetics, covered these spots with a single component solder mask. And finally, I shined ultraviolet light on it to cure the mask. This board is only a BMS board. It protects the battery from deep discharge, overcharge, short circuits, and overheating. It doesn't have balancing. There is an external temperature sensor. If you want, you can solder a second SMD thermistor onto the board. There are 3 shunts, and they're pretty good ones. If that's not enough and the protection kicks in, you can always increase the current by lowering the shunt resistance. The vulnerable parts of the board are sealed with factory-applied sealant. The only drawback of this and similar boards is the weak charging system. In this system, we have a pair of diodes connected in parallel and one small MOSFET. This board can handle a couple or 3 amps, but I wouldn't recommend more than that. But there's one thing. Charging is done through the standard round connector or the charging terminals. If you bypass all that, you can charge the battery through the power terminals with higher currents, but in that case, the BMS won't function and won't stop the process after the battery is fully charged. In that case, you absolutely must charge the battery with a stable current and a stable voltage not exceeding 21 volts, or else you'll be in trouble. Actually, don't listen to me and don't do this. It's dangerous and can have serious consequences, up to and including fire. Finally, I'll note that I had to trim the board a little so everything would fit perfectly in the case. Now, about connecting the components. I'm planning to draw short bursts of current from the battery at 50 amps and above, so the capacity of the connecting strips needs to handle that. The whole problem is that our battery is single-layered, and usually for these kinds of currents, people use 2-, 3-, or even 4-layer batteries. But I specifically want a compact, high-current battery. We'll be connecting the cells in series using spot welding, and for spot welding, I'll be using my own creation, the MyWeld version 2.0 Pro machine, equipped with 2 supercapacitors. If you're interested in the project, you'll find a link to the video in the description. This is a completely free project. I've made all the source files, boards, and schematics freely available, and many people have already replicated it. I highly recommend it to everyone. We're welding in automatic mode, 2 pulses. I'll be welding a sandwich structure. On the bottom, there's a copper strip that's 0.15mm thick and 10mm wide, and on top, pure nickel that's 0.2mm thick and 8mm wide. The cross-section for the nickel is 1.6 square millimeters, and for the copper, it's 1.5 square millimeters. In theory, that should be enough, but you can never have too much cross-section, so I welded another sandwich like that on top. As a result, the copper cross-section became 3 square millimeters, and the nickel is 3.2. The total resistance of the battery is now in front of you. At the end, we installed the protection board and solder it in place. Looks like everything is ready. We checked the output voltage and the total resistance of the battery, taking the board into account. Next up are the tests. First, we'll fully charge the battery through the charging terminals. We'll set the charge cutoff voltage to 21 volts. After charging is complete, I raise the voltage to check if the protection works. And, as we can see, the BMS board works perfectly. Off camera, I also discharged the battery, but not to determine its capacity. It's about 4.2 amp hours here, and that's been checked multiple times. I discharged it to test the deep discharge protection. And it works perfectly here as well. Now, regarding high current discharge. The discharge setup consists of a load resistor, a voltmeter, and a clamp ammeter. We're not going to mess around here either, so let's hit it with about 50 amps right away. At the same time, we're monitoring the temperature with a thermal imager. The temperature, of course, is pretty high, and it'll be even higher in a closed case. But nothing bad will happen, since we're not seeing any critical temperatures, and if anything does happen, the thermal protection will kick in. By the way, it works reliably. That was checked as well. 50 amps of current for a single-layer battery is, of course, pretty impressive. By the way, I even loaded it up to 60 amps, which is kind of a lot, but the battery handled it without any issues. I didn't risk pushing it any further. Obviously, for a short period of a few seconds, the output current can be much higher. Regarding charging with a current of 21 amps, I wish I could show you that, but in my lab I have more than 10 power supplies. There are both high voltage and low voltage power units with up to 70 amps, multi-channel, programmable, portable, ultra-low noise, linear, and switching types. But then I suddenly realized that I don't have any power supplies that can deliver currents close to 20 amps at 21 volts. However, in the relevant review, I showed how a single cell can be safely charged with such currents. So, there shouldn't be any issues with the battery either. But, of course, you can only charge with such currents by bypassing the BMS board, which isn't ideal. At the end, some areas of the board were coated with several layers of acrylic varnish. And the battery is ready. All that's left is to put everything together, stick on the labels, and enjoy the power of graphene. That's it for this video. If you enjoyed it, don't forget to like the video, leave a comment to support the channel, and if you feel like it, you can also subscribe to my other YouTube channels. All of that and other useful information, as always, is in the description. That's all from me. As always, this was Kazyanov K. See you next time. Bye!